on relational data. I wanted to take the messiest data I could find, which was from a brain-computer interface, and then take a very structured way to link it together. And I wanted to see how that would happen. So with all that being said, I was just brainstorming some different ideas, and this video is actually the patient from let me say that. All right, it's been about 6, 7 months since I presented at the hackathon in San Francisco, and I apologize for the time. Uh, as we'll get into it, there were some quotes I made, and I wanted to make sure that they were all right. And I had taken the data code and visualizations for the Brain to Text 25 competition, which includes a brain computer interface. So taking the messiest data I could find, and then take the foundation model for in-context learning on relational data that keeps everything in line and finds relations and relativity in messy data. So I wanted to see if I could take the messiest data, the structured data, put the two together, and see what would happen. So that was my brainstorming process. And this is a video from the Brain to Text 25, which isn't part of the competition, but it's part of what the researchers at UC Davis are working on.
Not being able to communicate is so frustrating and demoralizing. It is like you are trapped.
Communication is so important to our everyday lives. Something as simple as, I have an itch, or I'm thirsty, or I love you. Imagine not being able to say those things to the people that you care about most in your life. A brain-computer interface is a device that records brain signals from people that are paralyzed, and then translates those brain signals to allow people to communicate. So this research is happening as part of a clinical trial called BrainGate 2. The idea is people living with conditions like spinal cord injury, brainstem stroke, or ALS undergo surgical implantation of electrodes into their motor cortex. And thereafter, they work with a scientific team to develop next-generation technologies to help people living with paralysis. I recently implanted a 45-year-old man with ALS who really can't be understood when he tries to speak very easily. And by using a BCI, we can translate his desire to speak and have words appear on a screen.
In essence, what we're doing is we're bypassing the injury. We're recording from the source, from this part of the brain that's trying to send these commands to the muscles. And we're translating those patterns of brain activity into the phonemes, so that's like a syllable, the unit of speech, and then the words that they're trying to say.
Not only can we accurately decode the words that he's reading prompted off of a screen, but we can also accurately predict what he's trying to say in free-form conversation.
A lot of the demonstrations of BCI technology over the past few decades took weeks or months to get working. The first time he tried to use the system, it just worked.
Okay, ready?
That first time that he tried to speak and that word appeared on the screen, he started crying, I started crying, his family started crying. Basically everyone, we had to pause. We stopped the rest of that block of experiment trials. Everyone composed themselves. They were like, all right, let's do it again. And it kept working. So yeah, it was really special. It was a special moment.
At this point, we can decode what he's trying to say about 97% of the time, which is better than a lot of commercially available smartphone applications that try to interpret your voice, which hover around 95%. This is by far the most accurate decoding ever reported.
So it's not that we're reading people's minds. We're not detecting their inner thought or their inner monologue or even their mind's voice. We're really detecting their attempt to move their muscles and to talk.
People who do not have the ability to communicate well or quickly are often isolated and lonely. Having something like this will give them hope and opportunity to be more of themselves.
We've actually used artificial intelligence to mimic his own voice.
The easiest way to protect ourselves from mercury pollution is to limit our consumption
By using video recordings that were collected prior to him having ALS, we were able to digitally reconstruct his voice. So now when he tries to speak, not only do words appear on the screen, but it sounds like him.
It feels a lot like me. It makes people cry who have not heard me in a while.
I think we're at a point where it does work well enough that it really lets him just be a part of society and to talk.
I am able to still work full-time for climate action, and I am able to do that well and more efficiently with this device.
Honestly, the reason this is so transformative is because it provides hope for people living with these kinds of diseases, that as they face their disease, that they know that they will hopefully have the ability to retain communication.
I hope that we are at a time when everyone who is like me have the same opportunity as I do to have a device like this that will help them communicate. Let's all make that happen, okay?
So, as you can see, that is all of the work by the UC Davis researchers. They just had provided that data, and it is the neural signals to the phonemes. Uses a 5-layer GRU decoder, I believe, and then the best way to show that is they record it. They tried to use this implanted device to capture those signals. Those signals are then translated on another device. And then that other device translates it again, opens up a server, and then connects the two. And the words you saw on the screen was just a large coordination between signal reader, computer, and front-end application. So my question was, could Kumo's role in BCI data analysis focus and identify interconnected neural patterns and show evidence between artificial and biological neural networks? Down here, you can see this is what the researchers at UC Davis have done. So they have the Q words, which is the string, the Q phonemes, so they've broken those words down into phonemes, the decoded phonemes. So when he's trying to say something, what is he doing? And you can see, or what is he trying to say based off of the uh, the peaks and the valleys and everything else that's coming through that decode like that the current neural network, and then the decoded words and the decoded phonemes. So up and then back down. And looking at their data that they had presented, this side-based slice can show you which of the arrays are spiking, which of the arrays are producing which energy, and how that is impacting the patient. And here you can see the post-implant day 69. They had done a whole lot of days with these tests to see or correlate neural signals with the phonemes to help uh, improve the space, increase the science in there. So taking that, I thought, okay, well, it looks a lot like the 2024 Geoffrey Hinton's work with differences between artificial and biological neural networks, forward propagation, backward propagation, and okay, I'm just going to set myself up to understand different signal processing and the mediums for which those signals are processed. And here is a direct snip from that showing that the energy level, this is where I had kind of indexed it, the energy level and all of those peaks look like neural signals or look like signals, look like whatever. Right now, they're just peaks and valleys. It could be like, I don't know, anywhere you go. I'm living in Utah, so a lot of peaks and valleys here. But I thought, okay, well, if the neural network is being trained to drop in that one point, I wonder if it would be the same for the neural signals. And then observing what UC Davis had done, I looked here and you can see on the time, it kind of cut off because it just I wanted to like overlay it. But you can see on the drop, the different energy level from zero or yeah, from below zero, -20 up to 50. So the 50 would be the spike of the energy being exerted towards that. So I thought, oh, look at that. You can take the artificial neural network, which is on another layer, and it's reading from a biological neural network. So I wonder what the relationships are. And then I thought, okay, well, Kumo AI, the relational foundation model, they got to do it. They can make those. They can make that bitch happen. And through running that, I just had to set up the signals and read it into structured data, which was tough. At first, I thought I'm going to take the phonemes and see if I can take the phonetic spelling and focus that into the words, because that's the layer that the competition had been for the brain to text. I thought that would be in context. Well, what I found was it only increased the accuracy from the initial one that they had given us by like 7%. And after doing that, I ran it again, and I've been using Lambda Labs to try and make it happen. And it just wasn't working. I couldn't get past the 7%. So I thought, I wonder if I just zoom out a little bit and give Kumo a little bit more, like the relational foundation model, a few more features, a few more layers of context that they can draw coordination or correlations between. And by doing that, I separated it out and said, okay, well, they have these thresholds. I wonder if I could use it where every time it passes that threshold, it's true or false. And at that time, all of those values for that array that hit that threshold or activated would show. And it worked. I had to structure it up a little bit and see if I could get from every neural signal a phonetic relationship, which is tough because if you look at the word cat, or you look at the word, or you say the word cat, or you say the word cab, the word cat and cab activate the same muscles. So when I'm activating the same muscles, uh, it's hard for anyone to, for the brain to, for a computer to transmit that from brain to the muscles. Whereas in here, it's translating it from there to the computer. So it's just a different source, or different output to input, than it is for us physically. So it's not solving or ALS. It's not helping with it, but it could. And that's what I really wanted to study too, is if it could, because I'm trying to take values from discrete, make them continuous, but also have continual progress. So I had separated the tables into structures with neural events. This is the neural signals, events, peaks, values with the metadata. I used a timestamp, really helpful because it's immutable. You know, that's the one timestamp that one thing happened. And that's the amplitude it was at that time on that channel at that event. Uh, Kind of a FOMO experience, you know, all the other ones don't want to miss out. The subject ID, which I thought was interesting because if you have the subject ID, you could also link it to, well, what was he looking at that time? Where was he when he wrote that? What was the weather like there? What was the weather like on that day? What was he going through? What day was it? What things does he know before he reads cat or cab on the screen? And that's for further analysis, but it was interesting. Then the phoneme events. So when it was annotated, and then the error around that showed the phoneme label, start and end times, and the phonetic features. So what features, what words are phonetically spelled similarly, and then also how is he trying to say similar words? How does that match the phoneme to the word? And then the causal relationships. This was connecting the neural events to the phonemes with the temporal delays because there is a latency. Nothing can move at the speed of light, and with these Utah arrays, there's always a little bit of damage that happens when it goes on the brain. And the great researchers at Precision Neuroscience, forgive me if I forget one, BlackRock Neurotech, Neuralink, Paradromics, they are all working on less invasive, more conducive, more conducive chips that will read better, read faster, and match kind of that speed of thought. So in this, we had to filter for the plausible causal windows and then include the relationship strength metrics, which is what we saw here, which is one tiny slice of one trial in one day. What we see is something cool, that the confusion of the language model is also something that can be modeled. So just like when I walk up to someone like cute girl, I want to talk to her, hey, don't know what to say, and my confusion starts to fold. Uh, Same thing with the large language models. When they're trying to read it, like read the thoughts at the speed of the sampling speed. And so what I had done here was just take the time because I thought that's the one thing that these things can all spin around. Take the word, take the phonemes, and then take the confusion matrix. And by using Kumo AI's relational foundation model, you can see here from the trial 0000 that clean that up, folded together, and that entropy between those words could be a space or it could be a absence of like clean that up. It's just those transitions. I remember when I was learning German, one thing that was really hard for me was understanding where one word ended and where one word began. And I started to write down the words as people would say them. And I would go home, look them up in the dictionary, and couldn't find them. I come to find out I had been chopping up the words in a different way. And so this is kind of what that's doing. And under here, you can see the sill. So clean, that's about the same time that it monitored it. The sill is a silence. And so that's this whole uh, wave movement. And you can see here, it's also creating, if you can, I added in like the different features of the phoneme, what it is, what the word, what that letter is, a consonant, a vowel, how are those words being said, what's the pattern of speech, how did we develop a language that kind of ebbs and flows with our feelings and what we're trying to say, and the inflection with which we say it. And I have over here too. I love Gemini. I use theirs to like use their CLI to run through it, and you can see that it's creating these pools, it's creating these structures for the sessions, for the trials, for the neural events, and the phoneme mappings to weave through, just like we try to weave our words through, just like I'm trying to figure out what to say, and I don't know who I'm talking to when I'm making these videos, so I'm just trying to get it and cast a wide net and catch everyone that I can. And if you set Kumo up right with the edge cases, it will be that wide net for you. It'll catch those relationships that you might miss, and when you're running that same space later, if data has changed and you run the same query, you may get different results, and it may actually help you increase your own understanding of your own data for relationships that you didn't know were there, which is part of Hinton's work as well, with his what was it? The Boltzmann machine and the restricted Boltzmann machine with the hidden nodes and the known nodes. And those hidden nodes, which is another one that I've been studying in time, how many of those hidden nodes are being hit or how many of those are being missed. And then that's the confusion matrix that it's trying to come up with. So we've kind of matched it by using physics to find those wells, kind of do what we do, but it just sits and parrots and waits for us to do it. But you can use all sorts of predictive querying and just keep scaling out the layer or the scope. This one for here is with the consonants and vowels. And if it was predicted, if it wasn't, when it was predicted, and how it was anchored. And trying to line it up, you can see just bring it closer and the neural activity for that specific event and how it interacted. So kind of just like what I was saying. Like if you're nervous too, probably sending more brain signals, you're probably sending more energy to your head. You're not breathing as much. So when you're not breathing as much, you're speaking too fast and you're trying to get all your words out. And yeah, it just a whole lot of things we try to force through our energy that we have. And then you can use it for all sorts of other things. Like once it's set up, predicting the duration of the words in a sentence problem graph. And this is just one of the sentences, and taking that one sentence and however many times it came across that sentence in the entire study, which was 141 days, I think, long. They had tested the same words and they thought, okay, well, how can we get it to kind of line up with a linear regression in a way? But this was flattening it with Kumo, Kumo's RFM. There was improved performance with context. So this was synthetic context that I had added, where I took that subject ID and I took, okay, this person is interested in woodworking. If they're interested in woodworking and that is known before, then when they see woodworking, it would reallocate it or re-rank it based off of what they had known or what was known to them prior. And I had come up with this when I came into the challenge of trying to use a graph-based neural network for re-ranking and the neural signals as they were going up and down. I thought, oh well, that's great because cat and cab like it's great, it works. It's if you take that and compare it to the rest of the corpora that he was using, take it to the rest of the words in the trials, wonderful. Like then I thought, all right, if he's in New York, context, this is a fusion context. He's in New York and he says, hey, there's a yellow cat. Right? The machine would say, oh, cabs are normal to New York. Hat is not really ever yellow. How many people have ever said that it's a yellow cat? And then if you wanted to strengthen it even more on the opposite side, oh, Garfield is an orange cat who lives in New York. So the orange cat lives in New York. It can't be the orange cat and it can't be a yellow cab. It can't be a yellow cat and it's not an orange cat. So it's either a yellow cab or an orange cat because it's in New York and he's in New York. But what if it is a yellow cat, right? And how'd you know it? And that's where I had gotten, okay, well, how can we get the synthetic context better so that you're interacting with almost two different Kumo RFM instances and bridging the gap between both of them? And then this was based off of the recurrent neural network scoring, how well they had done based off of the different trials, and then the predicted phoneme error rate, which is amazing for for a researcher, especially in a clinical trial when they want to see how well their model did across all of the features, which variant of the model they used for which one, what features, like what differences they had put on Git for one over the other. and sequence those out and then test them across all to see what the comparisons are and how they've differed and then how they can be classified. We've got the sequence patterns. This is similar to what I was saying earlier with the yellow cat and the yellow cab, how they match, and you take the current phoneme, what it goes to the following phoneme, how often that happens, and the relational foundation model is estimating that. The heat map of the electrode activity. This is only one small part on one of the arrays, but how the activity is being binned according to the electrode number and where it's spiking. So this gives an even more accurate vision of where the energy is being fed or where the energy is being felt on the actual array. Got the confidence score of top prediction for each trial. So which trials were the best for least amount of errors. Uh, you can follow up with the feature extraction, the neural event rate, the array location, which ones were operating the best. Maybe one of them you want to know where it is, and I mean it's really hard what those guys are doing. It's really impressive, and they got to get it right, and they've studied a long time to get it right. And this is just meant to help. Can we get more features for them to know more about the things that they already know and match the AI to their research ability, just like matching phonetic spelling and speech to all the effort and work that we've ever put in. We've got confusion matrix. At first, this looks great because it's predicting the phonemes from the array. But if there was something that was a little bit off, or you had multiple, like one that, and this was just a little, like the little arrays, but once you get these larger pieces from BlackRock Neurotech that are mesh that go across multiple regions of the brain, this would help to know what the confusion matrix across those parts of the brain would be and how that would be. So then this is great because it's 100%. But if it weren't, that would also show you incredible insight into the region of the brain and the neural signals that are coming from a prompted phoneme or prompted stimulus, whatever it may be, whatever the researchers use it for. This is just some of the code to show you how I matched them and how Kumo used it to match on the foreign keys and the primary keys, forward and backwards, forward and backwards. Use the language studies on the corpora, see which words are most common, which words are next to each other, uh, how they're classified. Phoneme complexity on EDA. This is on the different. This was on the the length of the phonemes, how complicated they are to say, how verbose. I think I chopped it up with some sort of tokenizer. I can't remember what I had used for this, but the phoneme length and the complexity of that, how often they appeared, and uh, how many time steps it took for each one of them to see, oh, well, that one is actually a harder phoneme for someone with ALS. I wonder if that region has something specific about it that could help us better understand it. And research drugs, research surgical methods, anything of those sorts. That's that's for those people those experts to focus on. Session quality, with the completion rate, trial count versus complexity, phoneme diversity to say, oh, look, well, how different was our phonetic spelling? Something I find interesting about that bottom right is kind of converges, but how complicated can you actually make a sentence? How complicated is it to, or like, how complicated can a sentence actually be in the English language? And how many different transformations or combinations of correct output could we have from these large language models that we're training? See here, top 20 most common phonemes, top 10. And then I really want to link it with the AlphaFold 3 to say which of the nodes for the different diseases are being connected. And in this one, I linked the BrainGate study from clinicaltrials.gov with the proteins from Protein Atlas. I wanted to see which proteins were affected by which diseases, and then put AlphaFold 3 right in the middle of them to say, these diseases from these clinical trials were affecting these proteins, and those proteins are also available in the open FDA that showed the medicines that were being used to target those proteins or target those diseases. And Kumo just creates a stronger graph linkage between them. In theory, is what I thought. So that's what this is. Yeah, cross domain feature influence. Not too much here, just more of the same. Then different ways to move the blocks around and find connections, which is what you really want to do if you want to see connections that you may not know, or explore variables or explore features that you want to string around in another way against other inputs. You can do that. So the data is what you need, and then Kumo just kind of sets the paths and also creates and highlights new paths between them that you can use. And I recommend going and reading their paper. It is excellent, really explains in depth how it works and how you can use it in so many different ways and different use cases. It really is something that everyone should go and learn how to use. I don't think that it's all going to be generative, because once it's generative, there's going to have to be something that verifies it or at least strengthens it. Otherwise, it's just there. It doesn't have as much meaning, or it's disconnected from everything else, and it's just producing more of the same things that we have now, where large language models are trained on these large corpora. And the way I see it is that each time it's made a transformation from that, it's created a new probability or a new hypothetical of something that could be true that hasn't been activated yet. Creates a hidden node from the geometric shape at the beginning, and then it converges back once it's reached that level, so it can go and send it. Well, the way you use it and the way everybody uses it a little bit different. It's almost yeah, it gets a little competitive sometimes. I mean, between me and my mom, I'm like, yeah, this is how I use it. She's like, no, this is how I use it. This is how I use it. It's just back and forth, like a tennis match. So I wanted to see if this would work well with time, and indeed it did. I think the most impressive and surprising or humbling chart I saw was the folding of the words over time, because that would help with the latency and the speed of word to screen, or from the neural signal to the screen, which is the speed of thought, rather than waiting for it to go through and bounce around a lot of hoops through another computer, Redis server, and then appear on the screen. So I'd say go give it a shot. I've tried another one. I'm an economist by, I studied economics. I just graduated from Johns Hopkins, and we used it for interest rates, which in a way, different market signals. What are they signaling? How is it being used? What are the features? And the price is always variable. It's always bouncing around based off of the fluctuations of life and the fluctuations of things. and most importantly, by latency. So I thought, I wonder if I can use this same model in something similar. And yeah, I have. So I've been using it to see how interest rates are affecting specific companies and their debt and their ratios. So it's a very powerful model. You can use it in a lot of ways. Sets up those correlations. And I'd say, yeah, the relative features to the inquiry will provide a lot more detail and depth into what is happening in that context. And once you know what's happening in that context, you'll be able to recognize that context again. And that, I think, is the biggest strength of the Kumo relational foundation model. So with that, I'd say go get your API key, try it out, read the paper, and reach out to their team for demos. They've got a great team, very willing to help, and their model context protocol server is fantastic. That way you can access the same level of insight and trustworthy data, strengthened data, or strengthened output of data through your model context protocol. So it's right there when you need it. It's at the speed of it's at the speed you're thinking and the quickness of your typing. And that same kind of thing from quickness to typing to screen is what I think would be amazing to give someone like Casey from that video and other people, as well as using Kumo RFM to try and find a cure for those, and Kumo RFM and AlphaFold 3 and all these, and like the protein atlas and the clinical trials and the open FDA to see if there's the features in there that we're missing that weren't relative to that time but are in context now.